Now, uh, here comes the section capacity of members subject to bending. Now, let's start with this bending chapter, which has been covered in the chapter number 5 of AS4100 code. Now, as mentioned before, every checks like bending or axial or interaction has been categorized in two parts like section capacity and the member capacity. So as mentioned before, the section capacity is check is supposed to take care of any sort of localized failure like local element buckling, yielding, and whereas in the member capacity check is supposed to take care of the member strength as a whole. That means the failure of a member as a whole, like lateral torsional buckling, flexural buckling, etc. So this is a very nice and very methodical approach by the code, by which subdivide it into two different parts. One is localized check and one is the global check. Now, for the bending capacity of a member or a section, we will just discuss in this slides. Now let's first discuss on the section capacity, then we will go to the member capacity. Uh, the nominal section moment capacity, that is MS, refers to the flexural strength of the cross section. Now the designer for the member subject to bending, we need to satisfy this relationship, that is the design section capacity, that is the nominal section capacity multiplied by the factor called capacity reduction factor. The default value is zero point 0.9. An engineer have the choice to make any changes to it. So this value should not be less than the design bending moment or design moment. So one need to take care of that. The uh, the capacity, the strength of the section should not be less than the design action effect. So you have this simple check, and you need to just take care of whether this relationship has been satisfied or not. But Staad performs this check and just take care of this relationship. Now, this MS value, that is the nominal section moment capacity about the major or the minor axis, is the product of this yield stress Fy multiplied by the Ze. Now the Ze is a very important and pivotal role here. That is the effective section modulus. Now if you have worked on any other design codes like US code or some other code, uh, there might be some other approaches like they have got this stress factor, that is the Fy term. They are modifying this term and keeping the section modulus same. But here in the Australian steel design code, um, the section modulus is being modified, is being and multiplied with the Fy value to come across to the nominal section moment capacity. Now, the entire process of determining this ZE has been covered from the clause number 5.2.2 to 5.2.5 of the AS4100 code. Now, here you can see the table, that is the table number 5.2. This table is also known as the section classification table. We also see in some other codes, or the element classification table. So one need to just determine the lambda. There are, if you go to the clauses, you can see there are some formula to determine the lambda, that is the element slenderness value. And this slenderness value or the lambda value should be within these zones, like plasticity limit or element limit, or in other word, you can determine whether that lambda value is within the plasticity limit or the yield limit, and accordingly that can be classified as the compact section or the non-compact or the slender section. So we'll discuss with some working examples in future in my forthcoming session so that we can understand the exact workflow of this section classification. Now, um, let's talk something about the moment capacity of a member or the uh, member capacity. Earlier we were discussing on the section capacity, now it's the member capacity. Now, as we are in the member capacity, it is very important to understand that um, for the member capacity check, we need to check the limit state of a member as a whole. That means whether the member is susceptible to undergo some global failure like a lateral torsional buckling, or if it is the axial one, then flexural torsional buckling, whatever it is. So for that, the code coins these two terms like segment and subsegment. So basically, what happens, the in case of bending, whenever the member fails by the global buckling, most of the cases it's a lateral torsional buckling, right? So whenever the flange is under compression, it tries to buckle laterally and makes the whole entire member sway or buckle laterally. So for this, you need to understand what should be or what are the different definitions of the restraint, because restraints plays a very important role here, the lateral restraint. So as the code categorize the different restraint type, and it defines the two different terms like segments and subsegment. So you need to understand what exactly segment and subsegment, and Staad also identifies these two definition. So the segment is the portion of a beam between the fully restrained F or the partially restrained P cross section. The combination can be FF or PP or FP. But on the other hand, if it is a subsegment, then it can be defined as a segment can be further any segment that have mentioned. Segment can be further subdivided into smaller portion having at their ends, at least at the laterally restrained location L to the critical flange. So in a nutshell, it's something like if you have a segment and if you insert any where it between the length of that segment, any sort of if you impose any sort of lateral restraint, then the the length between the lateral restraint to the nearest node or the nearest restraint can be defined as a subsegment. So the restraint combination can be FL, PL, or LL. So it is very important to understand more of this can be found in the code explanation of this. Here is some illustration to just show you what are the different types of restraint in the beam. Some sort of partial restraint and the lateral restraint. You can see the C shown here is the critical flange. Now, the critical flange is also very important definition here. It is known as the flange that would displace laterally and rotate further if the restraint were removed. This is the compression flange of a beam and the tension flange of a cantilever. So basically, it's a critical flange means some element or some flange which undergoes some significant compressive stress, and it tries to buckle, but it could not buckle as a like actual buckling effect. It just buckle or sways laterally, and what we call it the lateral torsional buckling. But the critical flange is the point at which the flange that would displace laterally or rotate further if the restraint were removed You need to understand that if there would not have been restraint, then that flange would have buckled laterally. So that point we call, or that part, or that flange, or the element we call the critical flange. So the here you can see the C has been denoted as the critical flange. So the partially restrained is on the left hand side you can see, and on the right hand side is the purely lateral restrained. Now let's we will discuss more on this type of restraint in the forthcoming slides. Now here in Staad we have um, subdivided, or we have categorized the different restraint type as F, P, L, U, FR, PR, and C. So the F means the fully restrained, P is the partially restrained, L the laterally restrained, U the unrestrained, FR the fully and rotationally restrained, F, PR is the partially or rotationally restrained, and C the continuously restrained. Now the first one, that is fully restrained, is the restraint that prevents the lateral displacement of the critical flange of the cross section and prevents twisting of the section. Twisting means something twisting about its own axis, something like you are applying some torque on that. Now, the partially restrained P is a restraint that prevents the critical flange of the cross section from displacing laterally and partly prevents the section from twisting. So it's not the full restraint exactly, but it prevents the critical flange from displaced laterally and partly prevents the section from twisting. And the lateral restraint is something like the restraint that prevents only the lateral displacement of the critical flange without preventing the twist of the section. So you need to take a note here that this lateral restraint L is only for preventing the lateral displacement, but it won't lock, or it won't restrict any sort of twisting of the section. Now, U is something we call a nil restraint. It's something like a cross section that does not comply with any sort of F, P, or L, or we can call it the unrestrained, means there is no restraint at all. And the next one is FR, that is fully restrained, fully and rotationally restrained. And the next is PR, partially and rotationally restrained. Now, this FR or PR is very important. For example, the code defines different types of buckling condition, or different types of displacement that can be restricted. One of the displacement is something we call um, rotating about the minor axis, not about the major axis. So if you apply the fully rotational restraint by FR, then it would restrict any sort of rotation about the minor axis of the section. Similar way, you can apply the partially rotationally restrained if the rotation is not supposed to get restricted 100%, means some sort of some fraction of the rotation is being captured, and and remaining is allowed to undergo. And the continuously restrained is something like you have the critical flange restraint provided continuously by the concrete slab or the checkered plate, or any sort of a diaphragm or a timber floor, etc. So these all types of restraint condition can be assigned in Staad.pro, and you can simulate those restraint condition in if you and very importantly, this all features, all restraint condition can only be defined if you have invoked the, or if you have modeled it as a physical member, because this can only be launched or only be defined if you have invoked the P brace, and P brace definition can only be defined if you have clicked on the toggle on button of the physical member icon. So that is very important because as we have been emphasizing and giving more and more importance on the physical member design, so this features or this restraint can only be available if you are working on the physical modeling. Now, moment capacity of a member, that is MSX. Uh, it's not exactly MSX, it's MBX. MSX is the section capacity of a member. Now, MBX is the moment capacity of a member. Now, this, this suffix or prefix or this sort of notation has got its significance. If you can see that the bx, whenever it is b, that means it's something we call it as a member. Whenever it's s, it is a section. So this bx is actually the um, is derived from the section capacity multiplied with some factor. We call it the alpha s, that is the slenderness reduction factor, and alpha m is the moment modification factor. And very interestingly, this one term is reducing the um, uh, MSX value, and other term is amplifying this value. So you have to take care of both these terms to understand what is the net effect and how much your MSX has to be modified. So we will discuss on this what is the significance of this alpha S and alpha M.